Okay. So, yes, I'll continue with the deflection part. Okay. So, when you apply a load on a beam, it will deflect it, and this is the deflected part. Okay. And this deflected part, this curve is known as elastic curve. So, if you need to find, suppose, go through this line, the deflection is measured from the original neutral axis to the neutral axis of the deformed beam. So, this was the original axis, and this is the neutral axis of the deformed. The distance between two is known as your deflection, and it is represented by your y. It may be necessary to determine the deflection y for every value of x. Suppose your beam is of 6 meter. Okay, this beam is of 6 meter, and you need to find the distance at you need to find the deflection at 3 meter. Okay, so how will you find? So basic is that you need to find the equation of this elastic curve for different beam, simply supported beam, cantilever beam. You need to find the deflection equation first for this beam. Okay, once you find out the deflection equation in terms of x. Okay, suppose I got some 3x plus 6. Suppose I got deflection equation like this. So in place of x, I can place 3. That means if I place x equals to 3, that means 3 into 3, 3 into 3 by 6 will give me deflection at 3 meter distance. So understood? So you need to find the deflection equation. Once you have found out the deflection equation, then you can find out the deflection at this point. Okay. And as per IS 4555, IS 4556, maybe Junaid sir has told you about this. So in design, you need a code, Indian Standard Code IS 456. So as per IS 456, a designer should be able to determine deflection, that is Ymax is equals to L beam by 300. Your Ymax should not exceed this value. L beam by 300. L beam is that the length of the beam. Okay, suppose you have a 9 meter length beam, so 9 by 300 should your value, the deflection value should always less than this value. If it comes more than that, then your beam will fail and it is not suitable for construction. Okay, so along with deflection, there is one more word I have discussed. As you have gone, hope you have gone through the video. So deflection has a definition which says that which says that it is the vertical distance of the beam measured before and after loading. Okay, it is a vertical. It is a vertical distance which is measured before and after loading. So before loading it was zero deflection, and after loading it has some deflection. So there is one more word called slope. And slope is the angle in radians measured between the tangent of the elastic curve, between the tangent to the elastic curve and the original axis of the beam. So if I draw a tangent at this point, suppose this is the elastic curve, I'll draw a tangent. Okay, so it is the uh, angle between the tangent drawn to the elastic curve and the original axis of the beam. So this, sorry, not this. Yeah, this will be your theta. If I draw a tangent here, this will not this one. Okay, not this one, not this one. This one will be your theta. This is your theta. Theta says at what angle this curve has moved. Okay, at what angle this curve has moved. So this is your slope. What is slope? It is the angle in radians measured between the tangent to the elastic curve and the original axis of the beam, and is represented by theta. Okay, or you can say dy by dx. Deflection is represented by y. Okay, and slope is represented by theta, or you can say dy by dx. You can write dy by dx like this one, y dash. Okay, so basic integration part, you can write dy by dx as y dash. There is one more term you will get, d square y by dx square. You can represent this one as y double dash, like this. Suppose I have been given you I have been given you d cube y by dx cube. So you can write this one as y triple dash. Okay, so deflection is your y and your slope is your dy by dx, or you can write y single dash. Okay. So now you have, I hope this word is clear. What is deflection? What is slope? You can find the deflection, you can find the slope at any point by placing the value of x on the equation of this deflection curve. So hope this slide is clear. Now let's move to the next slide. So there's various methods for determining the deflection of beam: double integration method, moment area method, elastic energy method, method of singularity functions, and many more. But we'll concentrate on these two methods: double integration method and moment area method. Okay. So let's start with the double integration method. The deflection curve of the beam is this. The equation of that elastic curve is, general equation is EI d square y by dx square equals to m. So this is the relation between slope and deflection. Okay, and I have given you assignment to derive these equations by yourself and submit me at the end of this month. Okay, before the end of this month. So this is the general equations. You have to apply this equation in all types of beams and all types of beams with different loads. Okay, this is the general equation of that elastic curve. You have seen this elastic curve, right? This is the deformed curve. The deformed curve is known as elastic curve. So the elastic curve has the equation of this one. The deflection curve of the bent beam is this. In order to obtain y, that is deflection, the above equation needs to be integrated twice. Okay, so you need to integrate this equation twice to get the deflection. How? See, you have a term d square y by, forget about EI, okay, you have a term d square y by dx square. When you integrate this one, what you will get? You will get dy by dx, right? And what is dy by dx? It is your slope. When you integrate once more this one, you will get simple y, which is your deflection. Got this point? Got this point or not? Hope this point is, this is the equation of curve. You have to integrate this equation twice to get the deflection. How? See, when you integrate this square y by dx square, you will get deflection slope dy by dx. What is dy by dx? Our slope. And when you integrate this one once more, you will get y, which is our deflection. So please go through the derivation of this equations. Okay. This you will get the derivation of these equations from the bending equations I have discussed in the last class. Right, I have discussed the derivation of the, so that bending equation will be required in the derivation of this equation. So please go through the derivations. We'll get plenty of notes on derivations on over the internet, but you understand it yourself. In extra classes, I'll try to take the class for this derivation also if you don't understand. But please go through this derivation, understand, then write your assignment. So an expression for the curvature at any point along the curve representing the deformed beam. So they have derived. This is the concise manner. They have made the derivation very small here. So ultimately you will get the equation like this: EI d square y by dx square equals to m. So remember this equation. This is the general equation. Now you have to use this equations to derive the deflection and slope for other beams. So let's see. So what is the procedure? Integrating once. When you integrate this one, integrating once yields to slope dy by dx at any point in the beam. Integrating twice yields to deflection y for any value of x. Okay, as I have discussed, when you integrate that once, you will get the slope dy by dx. When you integrate twice, you will get a value of deflection. So the first basic, the bending moment must be expressed as a function of the coordinate x before the integration. So before the integration, you have to represent it moment with in the function of x. Differential equation is second order. The solution must contain two constants. So this is the basics of your integration maths class. When you integrate one differential equation, you got a constant, right? So you need to evaluate that constant value. Then when you integrate again, then again there will be one more constant. So you have to find out those constant values. That is about this line. So you'll understand when we'll do numerical. So let's. This is the sign convention. This will be positive bending. This will be negative bending. So let's come to the assumption and limitations. Assumption is that deflection caused by shearing action negligibly small compared to the bending. So this is a case of pure bending. We are not considering the shearing part. Okay. See, when we studied the shear force and bending moment chapter, we saw there is a shear force also, right? So now we are not considered about shear force or shearing forces. We only consider about we only are considering the bending. Okay. And deflections are small compared to the cross sectional dimension of the beam. So whatever you get, the deflection is very small compared to the cross-sectional dimension. If you get large deflection, you will be thrown out of your job if you are in the field. Okay, the deflection is very small compared to the cross-sectional. That means if your beam is 400 mm by 300 mm and the long is 9 meter, the deflection part will be very less. All proportion of the beam are acting in the elastic range. So they are assuming that your beam is in elastic range. So this elastic range comes from your, see, every class is related from one to another. Okay, you have stress strain diagram, right? We have discussed stress strain diagram. So in the stress strain diagram, the elastic range is when you apply a load, it will come back. When you remove the load, it will come back to its original position, right? Just give me a minute. Okay. So your all proportion of the beam are acting in the elastic range. So they are. It is assuming that your beam will it will, when you apply a load, it will get deflected, but when you remove the load, it will come back to its original position. So this is the assumptions they have made. And beam is straight prior to the application of load. So your beam was straight when you before applying your load. Please go through these assumptions. So now let's take an example. So there is a cantilever beam given to you. Okay, this is the cantilever beam given to you, and load is applied at the free end. Okay, so this is the moment equation. What is moment equation is that when if you go back to your previous class, shear force and bending moment diagram, what we do, we find out a shear force equation and moment equation, right? So this is the moment equation. See, if I take a section at x, okay, suppose this is my beam. I'm applying a load at this. I'm taking a section of x. Okay, I'm taking a section at x at the distance of x from here. So there will be a movement, anti-clockwise movement, right? So I'm taking the movement summation of all the movements equals to 0. So what will be? This is anti-clockwise, so minus P into L plus this load will give a movement, right? This load will give a movement at this. I'm taking this section, so this load will give a movement which is this is P, and this is the distance is x, right? So P into x clockwise movement equals to 0. So this is my moment equations for this beam, right? So that's how you have to find first moment equation for the given beam. Okay, from clear your shear force and bending moment diagram chapter, then only you will able to find this moment equation. So you have to first find out the moment equation for a particular beam. Simply supported beam with point load, simply supported beam with UDL. You have to first find out the moment equation. Then what you have to do, you know this, you know the equation of this deflected part is EI d square y by dx square equals to m, right? This is the equation. Now what you have to do, you have to equate this equation in you have to place this equation here like this. Okay, this is your movement equation of this beam. You know the deflection equation of a curve is this one. So you have to replace this m by your movement equation of that particular beam. Once you this is the equation you have to integrate to find out the slope and deflection. So I'm integrating once. So when you integrate this one, when you integrate d square y by dx square, what you get? Dy by dx. When you integrate a constant part, so you have to clear with your maths also. Okay, how to do integration, what you get. Okay, so when you do integration of a constant, you get plx plus when you do a hope this part is clear to you. When you integrate a single variable, it will give you x square by 2, right? So like p x square by 2 plus when you integrate there is a constant c1. So this is the basic of your math. So when you integrate once, you will get this value. Now you have to find the value of C1 at boundary conditions. Okay. What are those boundary conditions? What are those boundary conditions? So boundary conditions will be like this. That if you see the this beam at a deflection. See, if you see this curve, if you see this curve, suppose I'm taking this one as A, I'm taking this point as B. If you see at A there is no deflection, right? At A there is no deflection. So that is the boundary condition. That at A is your deflection is 0. Plus slope is also 0. If you make a tangent to this elastic curve, there won't be any angle because there is no deflection and slope. So at A your deflection and slope is 0, and at B and at B your deflection is maximum, right? At B your deflection is maximum, and if you draw an angle also there will be an angle. That is at B your deflection is maximum and slope is also maximum for a cantilever beam. So boundary conditions for a cantilever beam that at A your deflection and slope is 0 and at B your deflection and slope is maximum. Okay, let's see. So at x equals to 0, at x equals to 0, we know that our slope is 0, dy by dx is 0, right? Just we have saw the boundary condition at x equals to 0. If I am taking at x equals to 0, my deflection, my slope is 0. So I have placed the dy by dx equals to 0 here, and I got the value of c1 equals to 0. So again, so my c1 is 0. So my equation becomes for the slope is, for the slope my equation became ey I dy by dx equals to minus plx plus px square by 2. So this is my slope equation. Okay. Suppose I have been asked to find out the slope of at 4-meter distance. 6-meter, suppose take the overall distance is 6 meter. I have been asked to find out the slope at 4 meter. So instead, so place the value of x equals to 4 in this equation. You will get the slope at 4-meter distance. So this is my equation for slope. Okay. Now let's see. Now integrating twice. Now I'm integrating this equation again. So when you integrate dy by dx, you will get y. You have x. When you integrate x, you will get x square by 2. So minus plx square by 2 plus when you integrate x square, there will be. Hope this part is clear to you. When you integrate x square, what will happen? It will be x cube by 3, right? So again x cube by 3, 3 into 2 is 6, 6 plus there is a constant value c2. Now again you have to apply boundary condition to find out the value of c2. So again at x equals to 0, your y is 0, right? We have discussed boundary condition that at A, that is at x equals to 0, your deflection slope is 0 and deflection is also 0. Slope is represented by dy by dx, which is 0, and your deflection is represented by y, which is also 0. So I have applied this boundary condition in this equation. So I have placed this x equals to 0 in all the equations and I got c2 equals to 0. So now my deflection equation becomes this one, plx square by 2 plus px cube by 3. Okay, this is my deflection equation. So if I ask you to find out the deflection at x equals to 3, Just place the value of 3 in x position, you will get the deflection at 3. Suppose I have asked you to find out the deflection at 6 meter, that is the whole length. Suppose here the whole length is L. So replace this x value by L like this. At x equals to L, my deflection is maximum. See, the deflection is maximum at x equals to L. So I've replaced the x value as L and I got the deflection as CL cube minus CL cube by 3I. Why minus? Negative by 2. Okay, so this is my deflection for a cantilever beam and this is the slope equation. You can find the slope at any place. Suppose you need to find the slope where the maximum slope, that is x equals to L. Replace this x by L, you will get the slope also. Sorry, here. Okay. Any confusion in this part? Please type in the chat box any confusion in this part and I'll move forward to another example. Any confusion? Short in time, please reply. Till now at any, and please go through the video. I already this derivation in my videos also. I'm again continuing. What about others? I'm again continuing this part, so let me know. Okay. So I'll move forward. Okay. So now this is the bending moment. This is the now I'm taking the case of cantilever beam with UDL. Okay. So this is my moment equation. One more thing I want to share that I have we just take the six cases like simply supported beam with point load, simply supported beam with UDL, cantilever beam with point load, cantilever beam with UDL, and the four cases, right? And the one cases will be cantilever beam with UDL and point load and simply supported beam with UDL and point load. I'll share the 6 videos of these type of numericals if I get in. Okay, I'll share the 6 videos if I get somewhere. Go through those videos and understand how to find the shear force and bending moment diagram. Very, very important. Okay, that if you know how to find the equations for moment, then only this classes will be clear to you. Now, this is the moment equations of this type of beam, cantilever beam with UDL. Take a section at some point. Okay, this will be your moment WL square by 2 minus WL and the distance at you are taking. Okay, so this is the moment equations for this type of beam. You know the equations for deflection is the curve equation for elastic curve or deflection curve is EI d square y by dx square equals to m. Now what you have to do? You have to replace this m by the moment equation of this beam. Okay. Now this is my equation. Now I'm integrating this one once. I got this one. Place the value of boundary condition, same boundary condition at x equals to 0, your slope will be 0. So I have placed dy by dA is 0 and I found out the C1 value VL cube by 6. Now I have placed this VL cube by 6 here and I have founded the slope equation. So this is my slope equation. Okay, this is my slope equation for this beam. So you can find the slope at any point position of x. Now again I am integrating that one. I got this equation. Now use the boundary conditions to find out the C2 value. Place the C2 value in this equation. You will get the deflection equation. So this is my deflection of cantilever beam with UDL. And I can find out the deflection at anywhere. Suppose I know the deflection is maximum at the end of the beam, that is x equals to L. So replace that x equals to by L. I got the deflection which is VL4 by 80 times. Okay. So we have discussed these two parts. Please go through the derivation of this one once. Okay. I'll share the PPT. So now let's move to the simply supported beam. This is the simply supported beam with UDL. Okay. This is the moment equation. This is the moment equation for a simply supported beam with UDL. what you have to do? You have to replace this moment equation b by ei d square y by dx square. Now see what. Now can you tell me what will be the boundary condition for simply supported beam? At cantilever beam, we have seen that the boundary condition is that at the fixed end there will be no deflection and slope, and at the free end there will be maximum deflection and slope. Can you tell me the boundary condition for simply supported beam? As I have discussed already in my last video I've shared, but still, can you tell me where the deflection will be maximum, where the slope will be maximum? Can you tell me? Please interact in the class. Can you tell me what could be the boundary condition? Boundary condition means where your slope can be maximum, where your deflection can be maximum in simply supported beam. Anyone? No one? Just try once. Deflection will be maximum in, yes, good. What about others? At center. What about others? At the center of the beam. Yes. Slope is maximum. Slope is maximum at the end support. Deflection will be maximum at the center of the beam. Good. Slope is maximum at the end support and slope deflection is okay. Okay, good. See, at supports, right? At supports, the beam is it is pinned down, right? It has been hinged. So at A and B, that at supports, your deflection is very less. If you see the curve, there is no deflection at the support. So that is one boundary condition, that at supports at A and B, your deflection will be 0 and your deflection will be maximum at the midspan. Okay, so that is about the deflection part. Deflection is 0 at the supports and deflection is maximum at the middle part. And at C, there is no slope. That means at the middle part, suppose at this is the middle part, if I'm drawing a tangent, there it is not making any angle. So slope is 0 at the middle part. But if you draw a tangent this curve at the support, we'll get an angle, right? If you draw a tangent to the support, we'll get an angle. So at support, at A and B, your slope is maximum. There is a conversion. Suppose this is the deflection. I'm representing deflection by triangle and slope by theta. So at support and at midspan. So at support, your deflection is 0. Okay, at support your deflection is 0 and at midspan your deflection is maximum. But in slope case, at the midspan your slope is 0 and its support it is maximum. Okay, this is deflection, this is slope. So deflection is 0 at the support and deflection is maximum at the midspan. Okay, and at theta, see you are able to making an angle at the support. So this is the maximum at the support. But in the middle span, if you draw a tangent, there is no angle. So slope is 0. So that is the boundary condition for a simply supported beam. So I got the equation, integrating it, got a constant value C1, find out the value of C1 with the boundary condition C. Now this is dy by dx. So you will get to know which boundary condition you need to apply. So dy by dx we have to see where the dy by dx is 0. So dy by dx we know it is 0 at the midspan. So we have to take x equals to L by 2 dy by dx. So we have to replace this x by L by 2 and dy by dx equals to 0 to find out the value of C1. So I got C1 as VL cube by 24. So place this C1 value in this equation, you will get, so this is my the final slope equation. Okay, this is my final slope equation. Now again integrate. Okay, now again you know the deflection is 0 at the end, that is at x equal to 0, your deflection is 0, that is at supports you have deflection 0, so at x equal to 0 you have deflection 0. So place the value of x and y here, find out the value of C2, I got 0, place the value of C2 in this equation, and this is my deflection, final deflection equation of simply supported beam with UDL, yes, uniformly distributed load. So I know the deflection is maximum at x at the midspan, that is L by 2. So I got the maximum value as 5WL4 by 384 EI. This is the magnitude. They have replaced the negative sign. It is as it shows the negative sign. So that is, this part is clear. Now let's see simply supported beam with your point load at the midspan. Okay. So we know we are taking a moment equation. This is a symmetrical beam. You can take the moment equation from any part. Suppose I am taking this part 0 from 0 to L by 2. This is my moment equation, right? I have replaced the moment equation, integrated it, and same boundary conditions will be applied as in simply supported beam. Find out the value of C1. Then I have found out the value of equation of slope. Then again the same procedure, I have found out the value of deflection equation, and I know maximum deflection at the midspan. So this is my the value of simply deflection when beam is given as simply supported beam with point load. Okay. So this is all about, we have discussed 4 basic numericals. In the next class we will discuss the movement area method, that is the next method. So please go through these cases: simply supported with point load, simply supported with UDL, and cantilever with point load, and cantilever with UDL. Okay. So in the next class we will study the movement area method. So please write your roll numbers in the chat box, and if you haven't understood any part from this, please type in the chat box so that I can continue. Wrote everyone? Everyone wrote their roll number? Anyone left to wrote their roll number? Hope everyone wrote their roll number. So please join the class. Okay, Vika. So join the class. I'll text in 5-10 minutes. So please join the class. Okay.